What's up guys, and welcome to this video on question 5 of the 2017 supplementary exam. Okay, so this question, as you can see, focuses on forces, work, energy, and power. Okay, so let's get into this question. So a reverse bungee is a thrill ride where passengers are strapped into a capsule and are shot into the air by using a pair of strong bungee cords. Okay, and the cords can be considered massless. If you actually go YouTube, they're quite interesting, and a couple of them have actually broken, and yeah, it's quite an interesting device and looks pretty fun. But anyway, so then it says consider the cables at the bottom of the bungee at the lowest point right there. The cables exert a maximum tension at this point of 7,000 newtons per cable, and the cables are angled at 65 degrees to the horizontal at this point. Okay, this is shown in the diagram. Okay, so TA equals TB for the maximum, which is equal to 7,000 newtons. Okay, so I'm just going to put that in there. 7,000 newtons equals 7,000 newtons. Okay, cool stuff. Now let's get into the question. Okay, I'm actually going to take that out. Let's see. It says question 5.1. Okay, so question 5.1 says calculate the total upward force that the bungee exerts on the passengers at this point. Okay, so we're looking for the total upward force. Okay, so let's start off with a nice free body diagram of the information that we know. Okay, we know there's definitely weight, then we've got TB and TA. Okay, and both of these have got vertical components and horizontal components. Okay, and we also know the magnitudes. Okay, so it says the total upward force. Okay, so the force upwards is going to be T, okay, we also know that 65 degrees, 65 degrees. Okay, so it's going to be TA sine 65 plus TB sine 65. Okay, but TA and TB are both equal, so we can say it's 2 times the tension sine 65 degrees. Okay, so that's 2 times 7,000 times sine of 65. Okay, we're using sine because I want the horizontal component, I mean the vertical component. Okay, so I want this component right here, and that's why we're using sine. Okay, and the force, the upward force, can be calculated as equaling 12,688,31 newtons. Okay, and that's that, and we get ourselves 3 marks. Okay, 5.2 is a definition. Okay, so the definition of a resultant vector. So define a resultant vector. Okay, so a resultant vector is the single vector that has the same effect as the original vectors acting together. Okay, so that's just our definition. So a resultant vector is the single vector that has the same effect as the original vectors acting together. Okay, and for that definition we get 2 marks. Question 5.3. Okay, so question 5.3, calculate the mass of the capsule if it experiences a net force of 4,000 newtons upward at this point of release, or at the point of release. So calculate the mass of the capsule if the net force is 400. Okay, so how are we going to know? How are we going to do this? Okay, so we're going to say that the sum of the forces or we can actually say that F net, okay, is equal to, okay, so the net forces acting on this is going to be, looking at this free body diagram, it's going to be the force upwards, and we're concerned in the vertical direction. Okay, so the force upwards minus the weight from our free body diagram. Okay, so the net force is upwards, which we've defined as the positive direction, so we're going to say it's plus 4,000 is equals to the upwards force, which is going to be positive 12,688.31 minus the weight. Okay, so the weight can be calculated as 8,688.31 newtons. Okay, and that would be in the downwards direction. Okay, and we know that weight is mass times gravity is equal to 8,688.31. Okay, so we're concerned with okay, so we want to know what the mass is. We know that gravity is 9,8, so the only unknown is m, and so we can calculate the mass as equaling 886.56 kilograms. Okay, and that's the answer. We had to go through 2 steps there, so we get rewarded with 5 marks. Cool stuff. Okay, so it says at a height of 25 meters above the release point, so 25 meters above this release point, a different capsule of mass 320 kilograms has a speed of 19 meters per second. Okay, so we've been given a velocity essentially, we've been given a new mass, and we've been given a height of 25 meters. Okay, so again we have a definition. 5.4 is a definition. Okay, I'm not going to write this one out because it's a bit longer, I'll just say it. So basically we want to know the work energy theorem. Okay, so the work energy theorem states that the work done by a net force on an object is equal to the change in kinetic energy of the object. So from this definition, basically, we know that work net is equal to change in EK, change in kinetic energy. Okay, and work net, yeah, let's just put it in anyway, is F net times change in displacement is equal to change in EK. Okay, but the most important part is these two, but it's important to know this too. Okay, and we get ourselves 4 marks for the definition. Okay, so in most of my videos I may link a definition to an equation. Okay, and the reason why I do it is because before they ask, or before they make you use the equation, they usually just introduce it by making you give the definition. So it's important to know what equation goes with that definition. And they are usually the same thing. So it's just the equation in words. Okay, so question 5.5. Okay, calculate the work done by the net force on the capsule to get the capsule to this point. Okay, so we want to know the work done by the net force. Okay, so using the theorem, we can say that work net equals change in EK. Okay, so the work net equals half times the mass of 320 times the change in velocity. Okay, so it starts from rest, so we're going to go, let's say half mass times velocity final squared minus velocity initial squared. Okay, so the final squared is going to be 19 squared, which was given in the question, minus our initial at rest, which is 0 squared, which is still 0, and we get a work net is equal to 57,760 joules. Okay, and that's the answer there. So question 5.5, we get 3 marks. Okay, next question. Okay, 5.6, calculate the increase in mechanical energy of the capsule at this point. Okay, so we want to know the increase in mechanical energy. Okay, so we can say the mechanical energy, EMEC, let's say, is equal to change in EK plus change in EP. Okay, so EK we've already calculated as 57,760. Okay, plus EP is equal to mgh. Okay, the mass was given as 320. We know the value of gravity is 9,8. The constant and the height was given as 25 meters, if I'm correct. And yes, it was 25. Okay, so if we calculate this, plug it into our calculator, we get the the mechanical energy is equal to 136,160 and units of joules. Okay, so basically the increase takes into account the kinetic energy and the mechanical energy, and the reason why we're saying it's an increase is because we could actually say that this we worked with velocity final minus velocity initial, and this we could even say is height final minus height initial, and the initial height is being used as the datum of 0. So at the bottom it has no kinetic energy and no potential energy, so Emech equals 0, and when it's at the top right here, it's got a height of 25, a velocity of 19, and a Emech of 163,160 joules. Okay, so that's why that's the change in kinetic energy at the top. Okay, cool stuff. Question 5.7. Let's do it here. Okay, so question 5.7. Calculate the average applied force that the cables exert on the capsule to accelerate it to a speed of 19.16. So we want the average applied force. Okay, so what can we use here? Okay, so here we're using that the work net, or the we can use the work net is equal to F net change in S, okay, which is equal to the gain in mechanical energy. Okay, so the gain in mechanical energy was 136,160, and we know, so F net change in S, what is our change in displacement? It was 25 meters. It's equal to 136,160. So the only unknown here is F net, which is what we're looking for, the average applied force. So F net we can calculate as being 5,446,4 units of newtons. Okay, and that's the final answer, and we get ourselves 4 marks there. Cool stuff. Okay, then it says calculate the maximum height from the release point that the capsule will reach if the cable exerts no further forces on the capsule. The capsule is free to move upwards from the 25-meter point. Okay, so basically what it's saying is how high, so it's saying how high could this machine potentially go if it was able to go past the 25-meter point. Okay, so basically what we're trying to do is convert this mechanical energy into gravitational potential energy. So basically what we're saying is Emech is equal to, if it had no kinetic energy involved, or we can actually say is equal to EP plus EK, but at the highest point the velocity equals 0, so EP would be mgh plus half mv squared, but at the highest point, remember at the highest point the velocity would equal 0, so that entire term goes to 0. So where would Emech of the one we just calculated, so 136,160 is equal to mass of 320 times 9,8 g, and what height can we get to? The only unknown here is our height, so we can calculate the height. H is equal to 43,42 meters, and that's the height. Okay, and we get 4 marks there. And the last question, 5.9, is a graph. Okay, so the question says, sketch a position time. So we're sketching a position in meters versus time. Position time for the upward motion of the capsule from its release point, so from the bottom to its maximum height. Okay, show on the graph the height 25 meters and the maximum height it reaches. Okay, so we know that we need to show 25 at some stage. Okay, and we know that we need to show the maximum height, which was 43.42. Okay, so how are we going to get the shape of this graph? Okay, remember, so we can put a 0 point right there. Time is in seconds. Okay, remember, until it goes to the 25 mark, it's accelerating because it has the tension in the cable. So it's going to look something like that. Okay, thereafter we can assume that the tension in the cable goes away, so it's going to start leveling off until it reaches this point right here. So let's say it'll look something like that. Maybe that wasn't. Let's see if I can get it a bit nicer. Yeah, basically something like that. And you should be able to get your 4 marks for that. And basically we have tension here, and in this next section we don't have any forces, any applied force besides gravity pulling it down. So no tension, let's just say no tension. Okay, so we just have the gravitational force acting downwards on the capsule. Okay, cool stuff, guys. I hope you guys found this video useful. It's actually quite a long question, 32 marks, lots of marks. So yeah, thanks for watching, guys, and I hope you found it useful. Cheers.